Hello everyone, welcome to our discussion of the limit of a function. I hope you've already taken the opportunity to read through the section before watching this video. And I'm not talking about reading and understanding every sentence and every paragraph, but I hope you've taken the time to skim through the section before watching this video. So in calculus, let's give an overall basic definition of a limit. So in calculus, and this is not a formal definition, by the way. We will get to the formal definition a little bit later. In calculus, the limit of a function the value of the function approaching some quantity. So the value of the function approaching some value. Okay, so the key is to connect the word limit with the word approaching. Okay, that's what we mean. So let's just look at a very basic example of a limit. Suppose we ask the question, what is the limit of, let's say, this function, f of x equals x plus 7 at 2. Okay, suppose we ask that question. In plain English, what is the limit of that function at 2? So what this question is really asking, so it's asking what is the value of function f of x when the value of x approaches 2. So once again, this question, what is the limit of this function at 2, means what is the value of this function as x approaches 2. Okay. As x approaches 2. Again, I'm going to underline that word. Now, in this example, I picked a really simple example to just make sure that we understand what is meant by the limit. But we will get to more examples that are not so straightforward as this one. And you'll see what why it's so important to understand that limit is the value of a function as the input variable approaches some value. It doesn't have to be 2. X does not have to be 2. When we're taking the limit of a function at 2, x does not have to be have to take or have to be 2. It could be 1.99999, or it could be 2.11111, and it could be very close to 2 on either side, but not be exactly 2. And you'll see how that works in half an hour or so. Okay? So if that's the question, then we can convert this question from plain English to mathematical notation. So let's see how that is done. So using mathematical notation, which you will see a lot in all calculus courses, by saying that limit LIM signifies limit of function f of x as x approaches 2. Okay, so the x arrow 2 appears under the word LIM, or the letters LIM. Okay, and then of course this is equal to 9. Okay, a very, very simple limit here. So in this simple example, we want to notice 3 extremely important things in this course in general. Okay, so we want to put the spotlight on this. In this example, notice these 3 things. That 1, the value of that function f of x at x equals 2 is, at x equals 2 x equals 2 is 9. Okay, so that's the first thing. So that function at x equals 2 does have a certain value. Okay, that's the first thing we notice. Second, the value of the function or the value of, let's say, f of x as x approaches 2 from the left. From the left, that means 1.9, 1.98, 1.989, 1.999. So that's approaching 2 from the left. Or x approaching 2 from the left. That minus on top means x arrow 2 means x is approaching 2 from the left. And from the right it would be positive. Okay? From the left is 9. Okay? So just try that with your calculator. If you plug in numbers that are from the left, getting increasingly closer and closer to 2, x equals 2, the value of the function gets increasingly closer and closer to 9. Okay, you can quickly test that. By the same token, we can say that the value of this function as this time as x approaches 2 from the right, or x approaching 2 from the right, is 9 as well. So how do we approach 2 from the right? Well, pick number 5, x equals 5. Plug it in there, right? You get 12. Then pick 4. What do you get? You get 11. So you're getting, as you get closer and closer to x value 2, the value of the function f of x gets closer and closer to 9. Okay? Those are very important things that we need to notice now, and in section 1.5 when we will be talking about continuity of functions. A function is continuous. We haven't gotten that far yet, but since these 3 constitute what we call the continuity of a function. If one of these is not valid, if one of these is not the same number, then the function we say is not continuous at that point, which is a very important topic in calculus, because calculus does not like discontinuity. It likes continuity. So we need to know where the functions are continuous when they are not. Okay. So as these three refer to continuity, which we will look at in later sections, these two, if these two are valid, in other words, if you take the limit of a function from left and from right, and you get to the same number, then we say that the limit of the function exists and it's equal to 9. So let me just add a statement here that these last two, number 2 and 3, so numbers 2 and 3 refer to the function having a limit having a limit of 9 at x, or as x approaches 2. Notice when you don't put negative or positive on top, that automatically means that x is approaching 2 from both sides. So if we want to specify from which side we're approaching, the x is approaching that value, we put a minus on the upper right corner. So x is approaching 2 from the left, x is approaching 2 from the right, and if you leave it blank, that means x is approaching 2 from both sides. Okay? So of course, not all functions have a limit that is equal to the value of x, value of the function at that x value. Okay, so that's a very important thing to mention at this point. That is equal to the value of the function at x. What we mean by that is that, see, in this case, the function is continuous, and it has the same value. If you plug in for x with 2, the function is equal to 9, and if you approach 2 from left or from right, it has the same value. But that's not always the case. A function can have a limit at some x value, which is different than the value of the function at that x value. So we could have had a function that has, say, limit at limit of 9 as x approaches 2, but the value of the function could have been something else. At 2, it could have been, say, 4. Okay, so this idea of a limit really is about what is the value of the function approach as get closer and closer to as x approaches some value. Okay, you'll see more examples of this, so I'm sure you'll be clear as to how the idea of a limit of a function works. So we made a statement here, and now let's supply an example for it. Okay? So for example, consider this function, right? F of x, we have 2 plus x cubed minus 8 divided by x, right? This is a function. This is a rational function, right? So first, let's ask this question. So this idea is connected to this statement that we made, okay? We're giving an example for that. So suppose we ask, what is the value of this function of f of x at, you guessed it, at x equals 0, right? I'm sure some of you, if not all of you, are saying, no, that's not possible. Well, let's look at it. So the value of the function at x equals 0, if we plug in for x with 0, we have 2 plus 0 cubed minus 8 divided by x, okay? Or divided by 0, sorry. So let me make that correction. So this is 0. Would be equal to 8 minus 8 over 0, 0 divided by 0, and we know that at 0, at x equals 0, this function is undefined, right? 0 divided by 0, that means at x equals 0, that function is undefined, okay? But the question is, does the function have a limit at x equals 0? That means we're talking about limit, right? So we're not talking about x being exactly 0. We're talking about the x values that approach 0 from both sides. That's what it means to look at the value of a function at some x value. What happens to the value of the function as x gets closer or approaches some value? Okay, let's look at that. Because we know that the function value at x equals 0 does not exist, or it's undefined. Okay, so here's our second question then. So what is the value of the function? Or I should say, let me make the correction here, guys. Before I post these lecture notes on Canvas, I'm going to white this out and make it neater. But in the video, I want to, let's say, what is the limit of the function? Because we know the value of the function at x equals 0 is undefined or does not exist. So what is the limit of the function as x approaches 0? And let's specify from the left. Okay. So let's rephrase or reword this question using mathematical notation. So in other words, we're asking, the limit of f of x, 2 plus x cubed minus 8 over x, under the words or the letters LIM, x approaching 0 from the left, right? So 0 minus 0 from the left, like that. That's a question mark for us to answer. What is the limit of this function as x approaches 0 from the left? Okay, so let's do a table of values to answer this question. So we have, I'm going to draw a table here. Okay, so we want to say x approaching 0 from left. Okay, and on this side we're looking at the limit of the function f of x. Okay, so we have, let's pick some values. I've already done that. So I'm -1, -0.25. I've basically plugged in these values for x and calculated the value of the function as we get closer and closer to 0, and you'll see that from the left. So -0.015625, and then -0.0019531. Notice the values I'm picking for x are approaching 0 from the left, right? And then finally, I picked 5 values. So the last one, I picked -0.0001221. So the limit of the function as x is approaching 0 from the left are as follows: 7, 10.5625. Notice the trend in these values. What value are they approaching? So then 11.90649, 11.98829, 11.99927. So take a look at these values for the limit of a function. Are they approaching some value? As we get closer and closer to 0 from the left, from the negative side of the real number axis, are these numbers, these values of the function approaching some value? What value of the function are these approaching? If you said 12, you're absolutely correct. So let's state that the so the value of the function appears to be approaching 12. Okay? So we know that the function at 0 does not exist. But lo and behold, when we looked at the value of the function as x approaches 0, not that it's equal to 0, approaching 0 from the left, the function does have a value. It's approaching 12. Okay? It's approaching 12. All right. So what about, let's ask the question, what is the limit of the function as x approaches 0 from the right? Let's take a look at that. Again, I should correct this to limit. So what is the limit of the function as x approaches 0 from the right. So in other words, let's ask the same question using mathematical notation. What is the limit of this quantity? I just dropped the function notation, which is fine. So limit of this function as x approaches 0 from the right. So we have the plus sign in the upper right corner. Okay, and so that's the question we want to answer. Just like before, the previous page, let's look at a set of values, right? We can do that. We can pick some values and see values for x that approach 0 from the right and see how the function behaves. So x approaches 0 from the right. Okay, from the right. And we're looking at the limit of f of x, function f of x. Okay, that's my L. I hope it doesn't look like E, but that's L-I-M. Okay, so I picked these values that approach 0 from the right. I picked 1. I picked 0.5, 0.0625. Again, I picked just 5 values. You can, on your own, you can pick more numbers and see what happens to the limit of the function. 0.0039065. Notice these are getting closer and closer to 0 from the right. Okay, and one last one, 0.000488828, and then 19. Watch what happens to these values. As we're getting closer to 0, as x gets closer and closer to 0 from the right, what happens to the value of the function? Do you see the trend? So what value the function is approaching then? It's approaching 12 again, right? So let's state that. So the value of the function appears to be approaching 12. Okay. So what is the result of these 3 parts, these 3 analyses that we did? We looked at the value of the function at x equals 0. It was undefined. We figured that the limit of the function as x approaches 0 from the left was 12. We just figured out the limit of the function as x approaches 0 from the right is 12. So this is the final result. One, the function at 0 does not exist. Okay, and we said it's undefined, so which means it does not exist. Okay. The second thing we learned was that the limit of the function f of x as x approaching 0 from the left is equal to 12. The third thing we learned was that the limit of the function f of x as x approaches 0 from the right is equal to 12. So the function does not exist at x equals 0, but as x approaches 0 from the left and right, the limit from both sides approaches the same number. What does that mean then? What is the final conclusion of this? So the final conclusion is that the function at 0 does not exist, but the function as x approaches 0 does have a limit, and it's equal to 12. Okay, so therefore the limit of function f as x goes to 0 or approaches 0. Notice I didn't put negative or positive here. That means x is approaching 0 from both sides is equal to 12. Okay? So the function does not exist at x equals 0, but it does have a limit at that x value, which is 12. Okay? So there are several conclusions that we have to address at this point. Let's mention those. Okay, this is just writing in words the same conclusion that we just arrived at. Very important. It is possible for a function to have a limit at some value of x, even if the function does not exist at that value of x. We've just seen an example of that. Another note or another takeaway from this is that okay, very, very important. So the limit of a function at some value of x exists only if the limit from both sides exists. So in this example, if we approached 0 from left and we got, say, 12, but we approached 0 from the right and we got 4, then the function would not have a limit at x as x approaches 0. So in order for a function to have a limit, limits from left and right must be equal. Then we say that the function has a limit as x approaches 0. And that's what that statement is saying. So let's make the same statement in mathematically. So mathematically speaking then, right, we're switching back and forth between plain English and mathematical language. That's what I'm doing here. So mathematically speaking, we have if we say that the limit of a function f of x equals some value L as x approaches some value A, so this is a general definition, or saying this same statement generally. If that's the case, then the limit of the function f of x as x approaches A from the left must be equal to L, to the same quantity, and so that's not sufficient. This and the following must be true. The limit of the function as x approaches A from the right must also be L. Okay, if the limits of the function from both sides, from left and right, are equal to the same number, then the function has a limit as equal to L as x approaches that value A. Okay, all of these notes are very, very important. And I don't know, I want to box all of this, and I'm hoping not to have too many lines on these pages, but I hope that, but I do want to address that these are very, very important notes that you should remember. Okay. One thing that we should also mention is what happens when limit approaches infinity. So that would be another note, but I don't think I have enough space on this page, so let me move to another new page. So note, these are very important notes, so I want to box them in red box like that. So if a function approaches infinity, okay, if a function approaches infinity as x approaches some value A, or in other words, limit of function f of x equals infinity as x approaches A, then if that's the case, then the limit does not exist. So if the value of the function approaches infinity as x approaches some value, then the function has no limit as x approaches that value. The limit does not exist. Okay, if the limit should be some number, some definite number. It can't be infinity. Okay, then the limit does not exist. All right, so let's give an example of that, actually, to make it clear. So suppose if we have this graph, let's look at it graphically. And let me bring my ruler here to draw better straight lines. Okay, suppose we draw this graph. So here's our x-axis, here's our y-axis. And suppose we have a graph that looks like this. that goes like this. And also goes like this on the right. So this is the graph of the function f of x equals absolute value of 1 over x. Okay? That is the graph of that function. So, what happens to the value of the function? Because we know the function does not exist at x equals 0, right? Like before. If you plug in 0 for x, the function is undefined at that point. We know that. But does it have a limit as x approaches 0? Let's find that out. So this is the picture, but we want to know if that constitutes a limit. So the limit of function f of x as x approaches 0 from the left, right? What is it equal to? As we approach x0 from the left, the x value as it approaches 0 from the left, what happens to the function? It goes to infinity. It's equal to infinity. Okay, so the limit of the function f of x as x approaches 0 from the right, what is it equal to? So as x values along this graph, as x values approach 0, what happens to the function? It goes to positive infinity again. Okay, it's the same value, right? Infinity. But in the case of infinity, the limit does not exist. So limit of f of x as x approaches 0. Notice I left it blank, so I didn't put minus or positive. That means x approaches 0 from both sides. Limit of the function as x approaches 0 does not exist. Okay? So this is an example of what we said in the note above. Okay? Like that. Okay, so let's look at another case. I want to remind, earlier we said, I want to bring back this slide. See, earlier we said that, right? Earlier we said that the limit of a function at some value of x exists only if the limit from both sides exists. Okay? And I want to add to this, only if the limit from both sides exists and are equal to each other, and are equal to each other. So that's very, very important. Not only they must exist, but they must be equal to each other. So, and that's the mathematical way of saying the same thing, right? Limit from the left and from the right was both equal to L. What happens if they're not equal? The limit does not exist. So let's look at an example of that case. If the limit of a function as it approaches some x value from the left, does not equal the limit of the function as it approaches x from the right, then the limit of the function at that x value does not exist. So the key words here are that the limit from the left, and the limit from the right are not equal, does not equal, then the limit does not exist. Okay? Those are key things to remember. So what is an example of this kind of situation? Let's draw a graph and look at it graphically. So here's our x-axis and the y-axis, right? Or f of x. Let's call it y equals f of x, right? So suppose if we have this kind of situation, say if this is 2 and we have the graph moving that way, and at 1 we have the graph moving that way, right? Suppose this is the graph of a function that behaves this way. Then, graphically speaking, what do you see as we approach, and this is 0, of course, right? This is 0, 0, right there at the origin. So the limit of this function, the limit of f of x as x approaches 0 from the left is equal to what value? 1, right? It's okay if it's filled in circle or hollow circle, it doesn't matter. But it approaches 1. Whether it becomes 1 or not, it doesn't matter, but it does approach it. Okay, that's the idea of a limit. So there is a limit for this function as x approaches 0 from the left, that way, right? What happens as we approach 0 from the right? Right? So the limit of the function f of x as x approaches 0 from the right, from this side, it's equal to 2, right? As we approach 0, as I move along this curve, x values are getting closer and closer to 0, right? Because that's where x equals 0. So what happens to the value of the function? It approaches 2. So looking at the limit from the left and from the right, we don't get the same numbers. Mainly it's because of this gap, right? So therefore, in situations like this, then the limit of the function f of x as x approaches 0 from both sides, again, does not exist. Okay? I hope all of this is making the idea of a limit more understandable. So let's look at a numerical example of calculating the limit. We've been talking about it mostly generally and using graphs. So here's a numerical example. We ask, does the limit of function f of x equals x minus 1 divided by x squared minus 1, does that exist? Of course, as x approaches 1, right? Notice that we're not asking if the function value exists at x equals 1. That's not the question. Obviously, the function does not exist at this x value, right? 1 squared is 1 minus 1 is 0. So the denominator is 0. So we know the function does not exist at x equals 1. But does the function have a limit as x approaches 1? In other words, as x approaches 1 from the left and from the right, do we get the same? Does the function value approach the same value? If it does, the answer to this is yes. If it doesn't, the answer is no. So how do we show that numerically? Well, this is how. So we have, first, let's factor the denominator. So f of x is equal to x minus 1 divided by, we can factor this, right? X plus 1 times x minus 1. So this x minus 1 and this x minus 1 cancel each other out. We get 1 over x plus 1, right? So we can ask, this question, we can ask it with this, because after simplifying, this reduces to this. So then the limit of 1 over x plus 1 as x approaches 1 actually approaches this quantity. 1 plug in for x with 1 over 2. So yes, so the answer is yes. That's the limit does exist, and it's equal to 1/2. Okay, we couldn't do that in the beginning because it would make the denominator 0, but after simplifying, we can find the part of this original expression that can help us identify the limit if it exists. Okay. And I know I said this in words, but let me mention this for the sake of your notes. Let me write this down as a note to wrap up this solution, that the function has a limit as, let's say, as x approaches 1. But the function is not defined or does not exist, is not defined at x equals 1. So I hope you're catching the difference between the value of a function at some x value and the limit of a function as x approaches that same value. Okay, there is a very important distinction there. So here we have, in the next example, we have a graph, and we need to look at the graph and answer some questions based on that. So I think I can fit all that on this page here. So so here's an example. So given the following graph, let's draw it here. This is x, and here is the y-axis, or f of x. Then let's increment this to 1, 2, 3, 4, and 5. I may have picked my increments a little bit too large. 1, 2, 3, 4, and 5. Okay, so the graph, and this is 1, 2, 3, 4, and 5. Okay, it got a little bit crowded there, sorry, but I hope it's clear. And the graph is as follows. So we have right over 3 and 2, we have point there, and then we have right here, we have some point here, and this line goes like that and comes back to that. And then another piece of this graph starts here and let's say here at 4 and 4, like here, like that. So, and then like that, and then finally like that. Okay, so this is the graph we are given, and the questions are as follows. Part A, we want to know the limit of this function. This is whatever that function we have. Limit of f of x as x approaches 2 from the left. Okay, so as x is approaching 2 from the left, right? With this piece, it doesn't have a value because it's a hollow circle. So along this piece is not defined, but along here it is defined, right? As we approach 2 on this piece, it is defined, and the value is 3 right there. So that the value of the function, the limit of the function as x approaches 2 from the left is equal to 3. So this would be 3. And so, well, this, I forgot the question mark here. So that was the question mark. And then part B, the limit of the function f of x as x approaches 2 from the right this time. So as x approaches 2 from the right, from this side, this point suggests a limit where the function is approaching from the right. This is not the limit of the function, but from the right it does have a limit, and it's equal to 1. Okay, so that's 1. Part C, we want to know what is the limit of the function as x approaches 2, right? So this was from the left, approaching 2, x approaching 2 from the left, x approaching 2 from the right, but x approaching 2 from both sides. What is the limit? From the left, we got 3. From the right, we got another value, not equal. So the limit of the function as x approaches 2 does not exist. Okay. Then part D, the question is, what is the value of the function at 2? So notice there is no limit here. Right? What is the value of the function at 2? It is right there. It is 3. Right? So 3, which is equal to the limit of the function from the left, as x approaches 2 from the left. So E, notice so this is these limits that exist, these are one-sided limits. Okay, so the one-sided limits from the left and one-sided limit from the right do exist. But for the entire function to have a limit, the one-sided limits must be equal to each other, and that's not happening. So therefore, the function does not, the limit of the function as x approaches 2 does not exist. Okay? The one-sided limits exist, but the limit of the entire function does not exist because the one-sided limits are not equal to each other. Okay, so in this case, limit of the function as x approaches 4. Okay, so that's the question for this one. So as x approaches 4 from the right, that means, see, then 4 negative or 4 positive, that symbol is missing. That means they want us to calculate or show the limit of the function as x approaches from 4 from both sides. So 4 is right here, x equals 4 is here. As we're approaching it from the left, the function value is 4, right? We're approaching 4. The function doesn't have a value at that point. There's a gap there, there's a hole there, but we certainly approach it. We certainly approach 4. From the right, again, as you approach 4 along the x-axis, the value of the function also approaches 4. So this would be 4. Okay. And finally, f, what is the value of the function at 4? So they're not talking about the limit here, but the value of the function at 4. What is it? At 4, the function has no value. It's a hole. It does not exist. So, does not exist. So the function does have a limit as x approaches 4 from both sides, but the function itself does not exist at x equals 4. Let's look at another example, another graphical example, that is. Okay, so here's the function we are given, and it is a piecewise function. And so we have f of x equals 1 plus sine of x. So this is from our trig class, right? If x less than 0, cosine of x. If x is between and equal to 0 and pi, and sine of x if x is greater than pi. Okay, so if you were my student when I talked about drawing piecewise functions back in pre-calculus, I said that initially when you are given a piecewise function to graph, you want to cover the conditions, the ifs. You want to cover these. And you want to graph these very lightly with a pencil, which I'm going to grab in a second here. You want to draw these very lightly with a pencil, fully, and then after you've drawn each of these very lightly, then you want to go back and look at these conditions and darken the areas of solution and erase the other pieces. So I need to do that. Let me grab my eraser here, and also, did I bring my pencil? Yes, I did. So like that, okay? Because I'm going to erase those extraneous parts of my graph. But initially, I'm going to ignore all those ifs. I'm going to pretend that they don't even exist, okay? So here's our axes, first of all. So we have the x-axis, then we have the y-axis, or f of x and x, right? Okay, so with my pencil, and let me draw guidelines here. So I want to stay within those, because when I don't draw these, I'm not pretty good at keeping where my lines where they ought to stay. So that's, again, these are very light guidelines for my graph. So that's 1, that f of x equals 1, and I'm going to draw another one on top of that. So this would be 2, so 1, 2, and then I'm going to draw in just one guideline here on the negative side of the y-axis. Okay, very lightly. Okay, so we know that from trigonometry, we know that sine of x oscillates from 1 to -1, right? But this is 1 plus sine of x. So let me see if I can have a scratch paper here. So this quantity, this piece, so this is my scratch paper, please ignore that. That piece is, sine of x varies between 1 and -1. So 1 plus that varies between 1 plus 1 is 2, and 1 plus -1, 0. So that function, f of x equals 1 plus sine of x, varies between 0 and 2. Okay? So we want to do that. We want to show that here. Let's see. So I want to draw, let's see, so 1, 2, and then this would be like that, and so 0, so it would be something like that, so like that, and I should curve that much smoother here. It's curving like that, comes back, and then like that, and then like that. So this is what I wanted to draw, those parallel or horizontal guidelines, so I can stay within those. And on the left, that function, 1 plus sine of x, varies between 0 and 2. Okay? So, and then it goes back up again to that, and then comes back again like that. Okay? So this would be, and I meant to draw this much lighter than I did, But it's okay, I'll erase whatever doesn't belong there at the end. So then, let's graph this piece, cosine of x. Well, cosine of x, as we learned in trig, varies between -1 and 1. It oscillates, the amplitude of this is from 1 to -1. All right, so then let's draw that. I'm going to start here and go like this. So like that, and then curve back up and go through like that, and then like that, and then curve back down again and do that, and then like do that again. Okay. Geez, these are much darker than I meant, but it's okay. We will erase whatever doesn't belong there at the end. So this is the cosine of x graph. This is 1 plus sine of x. And then we have one more left, right? The sine of x. And that, as we learned from trig, it also varies between -1 and 1. So let me do that. So I would start from here. And then, let's see, if I want to draw these as best as I can. So it's like that. I think that's good enough. And then, like that. Did I draw that correctly? Let's see. Like this, and like that. Okay, so this is, I need to correct this a little bit. So it was a little bit out of place. It still is. Let me correct that. So that was the cosine of x, and that's better. That's a little bit better. And then go like that and do that. Okay, so now these, let me label these so they're more clear, and then I'll erase some things here. So that one is f of x equals, move this up a little bit, f of x equals sine of x, and this piece, that piece is f of x equals cosine of x, and that piece is f of x equals 1 plus sine of x. Okay? All right, so these are the graphs. As a matter of fact, on this side, the cosine of x, I didn't continue it, but we could continue it. So it would be, let's see, we could just come here and do like that. Do like that. I'm hesitant to draw that because I'm going to have to erase it anyway, but it's okay. We'll erase it like that and like that. Okay, so now looking at this function, this big curve that goes from 0 to 2, should exist only for x values that are less than 0. Okay, if x is less than 0, that means that piece, then this is the graph. So that means I'm going to graph, use my thicker marker here, and I'm going to put a hollow circle here, like that, and then I'm going to thicken that line. like that. Okay. And then I'm going to erase the rest of this. But I'll do it at the end. So that's that piece. And then for cosine of x, which is that one, this one that does that, that's the graph when x varies between 0 to pi. Where is the pi? Pi is where the cosine of pi is equal to -1. So that is pi. Okay, so I'm going to draw a dashed line here and say that's pi. So that's 0, that is pi. How do I know that? Because that's where this curve is -1. Cosine of pi is equal to -1. We know that from trig, right? So therefore, I'm going to draw this in red, the inside, and all the way to here. And I'm going to put a dot there as well. Okay? So I'm sure you can see that we need to erase this piece. All of this needs to go away. Okay? Like that. I'm afraid of smearing all this colors over the page. I try not to. Okay, so the last one is sine of x. Where's that happening? That's happening after, not at x equals pi, but after, for values of x greater than pi. So that would mean beyond this point. Okay, so let's draw that. I'm going to draw that with a different color. Let me use my black ink here. So at pi, where is the sine curve? Right there. Sine of x curve is right there. Right? So that is valid after x equals, for values of x that are greater than pi. So I'm going to put a hollow circle there, and then I'm going to draw the rest of this curve. And it's going to continue, but I'm going to end like that. I'm going to stop there, but let me put an arrow indicating that it's going to continue that way. And also I'm going to put an arrow at the end of this signifying that it's going to continue from that side. So any line that is pencil line that is not one of these bold-faced lines should be erased. Okay, they don't belong there. Okay, so all of that. Without these parallel guidelines, my graphs are pretty bad, so I need them in order to keep my graph a little bit more to scale and in a way that makes sense. Okay, and that too, that piece right there should go. I think that's good enough. So that's not bad. Like that, all of those extraneous lines should be gone. So only the bold-faced or colored lines are the valid pieces of this piecewise function. The pencil drawings are not valid. Those are. Okay, so now that we have that, what else they're asking us? They're asking us to determine the values of a for which limit of this function as x approaches a exists. Well, the limit of the function at almost all values of x exists. Almost any value of x you pick, the limit is going to exist. At this point, yes, right there. So that would be 1, and that is 2 right there. And this was -1. Does it exist anywhere here? Yes. So it exists for almost every place except one place. There's a place here on this graph where the limit of the function does not exist. Do you see it? Do you see where that point is? It's at pi, right? Right here. Because as x approaches pi from the left, what is the value of the function? -1. As x approaches pi from the right, what is the value of the function? 0. It approaches 0, right? So the two are not equal. -1 and 0 are not equal. Therefore, as x approaches pi, the function does not have a limit. But everywhere else, it does have a limit. So let's write that down. So we can generalize it like this. Limit of the function f of x exists for all values of x equals a, except this is key, except a equals pi, because we can then rationalize this answer as follows. Limit of f of x as x approaches pi from the left is equal to -1, right? -1. Limit of the function f of x as x approaches, I'm trying to keep everything on the screen, as x approaches pi from the right, it's equal to 0. Okay, like that. From the graph we can see that. Therefore, -1 is not equal to 0. So basically our answer is this, that for all values of x equals a, there is a limit except for pi. Okay. All right. So let's see another example of showing limits. So we just, a few minutes ago, we saw an example where there was a graph and we had to answer some questions, right? This one, I'm talking about this one, right? So now in this example that we're going to do now, these are given to us and we're expected to look at this information and draw the graph for that. Okay, so we're going the opposite way. Okay, and here are the conditions. For an example of a function f that satisfies all the following, I should correct this, guys, satisfies all the following conditions. And here are the conditions. And it should satisfy all of them, not one, all. So one of the conditions is that the limit of f of x equals 2 as x approaches 0 from the left. Limit of f of x should be equal to 0 as x approaches 0 from the right. Limit of f of x equals 3 as x approaches 4 from the left. Limit of f of x equals 0 as x approaches 4 from the right. And then also the value of the function at 0 is equal to 2, and the value of the function at 4 equals to 1. Okay, so we have 1, 2, 3, 4, 6 conditions to meet. So where do we start? When you have a problem like this, you always want to start from these two first. So plot these 2 points in your graph. Then draw these limits, the graph, so that these limits make sense. But first, you want to start with the values of the functions that are given, where you know the function exists at these 2 points. So let's do that. I'm going to draw the axes first. So we have, I guess that would be okay if I did it here, like that. This is x, and then for the y, like that. And that would be our f of x, like that. Okay, so let's increment this. Maximum x value that we have is 4. So I'm going to increment everything all the way to 4 on this axis. So 1, 2, 3, and 4. And for the function value, the highest one, the largest value is 3. So I'm going to increment 3. 1, 2, and 3. Like that. Okay, so the first thing is we want to plot these 2 points. So at 0, the function is equal to 2. So I'm going to plot that right there. That's that point. Then this one, at 4, x equals 4, the function is 1. So 4, x equals 4, and then 1. Roughly, it would be roughly here. Roughly there. Okay, so those are the given points. Now let's draw that. And it doesn't, after we plot these two, it doesn't matter where we start. So let's start with this one. As we approach, as x approaches 0 from the left, that means here, going in this direction, the value of the function approaches 2. Okay, so we can simply draw a line like that. Something like that. It's acceptable. As we're approaching x equals 0 from the left, the value of the function approaches 2. In fact, we are told that at 0, the value of the function is 2. So there you go. All right, so we're done with that. Next one, limit of the function f of x as x approaches 0 from the right, it's equal to 0. Okay, so we know that at 0, the function value is 2. So this is a limit, not a value. So I have to put a hollow circle here. Okay, I'm not filling this one in. Why? Because the function at 0 is equal to 2, not 0. So I'm going to leave it hollow like that. So this is just a limit. As we approach from 0 to 0 from the right, the function value is approaching 0. So we know the next line I'm going to draw, it's going to be like this, right? Or it's going to be on that side. But how far should I go? Let's look at other conditions. limit of the function as x approaches 4 from the left is equal to 3. So that would be that line then. So the limit of the function as x approaches 4 from the left, 4 from the left is equal to 3. So right there, that's 3 all the way here, and I'm going to put a hollow circle here. Why a hollow circle? Why not a full filled-in circle? Well, because we know at 4, the function value is equal to 1. Right? It can't be the other value too. At x equals 4, the function has just one value, which is that. So it can't be, this cannot be a filled-in circle. It has to be a hollow circle. But the nice thing about it is that now I can draw a line from here to here. But can I? Let me look at the last condition here. The limit of the function as x approaches 4 from the right. So that's 4 approaching 4 from the right. So it has nothing to do with 4 approaching from the left. So yeah, I can draw this line. I can draw this line like that and connect it to that. That's no problem. Okay? So I drew it smoothly like that. It doesn't matter if it's a straight line or if it's a curve. That's okay. So then, approaching the limit of the function as x approaches 4 from the right is equal to 0. So then that means that we should have a hollow circle here. Why? Because at 4, the function has value 1. Right? So we know that that point is 4, 1, and that point is 0, 2. So the limit of the function as x equals 4 approaches 0. So I'm going to put a hollow circle here, and then it doesn't matter. You want to draw a line there, so you can also draw it like that. Either way, it's fine. Like that, and like that. Okay, so as we approach 4 from the left, from the right, the value of the function approaches 0. Approaches 0, right? But at 4, the function value is 1, which is that point. Okay, so that's the graph that satisfies all those conditions, limit conditions. So those of you who are not math majors can stop here. You don't have to watch the rest of this video if you are not a math major. But if you are a math major, you should watch the rest of this video. So for those of you who are not math majors, the rest of this is optional. But for math majors, please, by all means, continue watching until the end of this video. Okay, so epsilon, I'm sure the math majors know this, that this word corresponds to the Greek letter like that. That's epsilon. And delta has this notation, that shape, that figure, in the Greek alphabet. Okay, so this would be the epsilon delta definition of a limit. And I want to write down quickly, if you are a math major, continue watching. optional for all other majors. So it'll be up to you. Okay, so let us consider our previous example. One of the examples that we did was the following. Consider the previous example of the limit of this function, 2 plus x cubed minus 8 divided by x, which we decided or we found that is equal to 12 as x approaches 0. Okay, this is something that we worked on. Now this result, as you saw from the graph that we just did, has a geometrical interpretation. If you have a function that has a limit at some value, that has a geometric interpretation. Let's draw that graph. So I want to, so this is the result that we had. And let me add, before I draw the graph, so the above limit has a geometric interpretation. And we want to draw that now. Okay. So let's draw that. I'll try to fit the graph here because I need the rest of the space here. So I'll do my best to draw it here, right there. It's kind of squishing my graph in the corner here, I know, but I need this space here anyway. So that's why. So we have this f of x function, and we have this x. And this function has a graph, and that goes like this. So 1, 2, 3, 4. It has a limit of 12, right? So let's draw that. 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12. That's the point, 0, 12, and then 13, and so on. 13, 14, 15, and so on. And then on this side, we have 1, 2, and 3, like that. So if we graph this function, roughly, it'll be, and this is the point -3, 3. I'll try to draw this as smooth as I can. And so that's 0, 12. So this graph would look something like this. Like that. And it should go through 0, 12 there. I mean, it doesn't go through. That's the whole point. The function has a limit there, but it does not exist there, right? We know that. And so if you plug in for x with 0, you end up with 0 over 0, which means the function should not exist. But that hole in the graph is so tiny, the limit exists at that point. So the line continues until 0.0000001 from the left, it exists. So you'll see it as a solid line going through, but in fact, there is a tiny gap there. There's a tiny hole there that is not visible. So let me point to that. So there is a tiny hole that is not visible. Okay, but the line looks like it's going through it, where in fact it doesn't. I mean, let me switch to computer so you can see a computer-generated version of this graph, and you'll see exactly what I mean. Because even the computer shows that the graph at that location does exist, that it does go through 0, 12, but in fact, it doesn't. There's a gap, there's a hole there, because at x equals 0, we showed that this function does not exist. As I switch from dock camera to computer, just so you can see this on a computer, you'll see your screen is going to blank out. So everything is okay. This is happening because of the switch. So let me switch to the computer. I'll do it for a second. Now it should blank out. Now it should be back. So this is the computer graph of the same function. It looks like it's going through 0, 12, where in fact it shouldn't, because there is a gap. So I just wanted to show you that, because even with a computer, you're going to see that that line looks like it's going through that, but in fact it shouldn't go through that. Okay, so with computer, the idea of a limit, we can find out gaps where even the graphs don't really show that to us. So with the idea of a limit, we can show that the function, whether it has a limit or not, at some x value, where the function itself does not exist at that x value. Okay, so then I mentioned that this is a geometric interpretation of the limit, so let's see how that works. So if we draw let me do that with my red pen here. So as x approaches 0, there is a limit, right, which is equal to 12. So on this side, I guess I better draw the horizontal lines here. So around that point 0, 12, let's take any small distance, and this is an arbitrary small distance of epsilon. So epsilon above this point and epsilon below it. Okay, so and I'll draw the other one with a different, the middle line with a different color. I know it's getting crowded, this graph, but it's okay. Okay, your book does an excellent job of this too. So if this graph becomes too crowded, then you can also look at the one in the book. But suppose we take a distance of epsilon above and below that point where there is a limit, right? Where we expect to have a limit. So let's take that as epsilon here and epsilon here. So equal, it doesn't matter how small this epsilon distance is, but it should be equal on either side of that point where we have a limit, where we expect to have a limit, right? So let's say that, think about any small distance epsilon any small distance epsilon away from that 0 point, from that point, 0, comma 12. Okay, on either side. And this is, we'll take this on either side. So for the limit of this function, to exist at that point, and we'll do an example after this, to exist at x equals 0, so you will always be able to find let's call this delta. So if this is epsilon, let's call this delta, right? And this is epsilon, and then let's call it delta. Let me draw this. So on either side of x equals 0, and I'm going to, once again, I'm going to draw this. Well, let me draw it with a different color here, with blue, I would say. So like that. And on this side, and that's that. So delta would be on either side of x equals 0. So that piece and that piece, that's delta, that is delta. Okay? That's a distance, that's a neighborhood, as I call it, a neighborhood on either side of x equals 0. Let's call it delta. So that's equals distance. And you can take this as small as you want. Okay? So for the limit of the function to exist at x equals 0, you will always be able to find some neighborhood on either side of x equals 0. Okay, so that let me move this up such that to a function value f of x within a distance within a distance epsilon, of the point 0, 12. Okay? So, in order to make what I just said in this paragraph understood, in order to make this clear, let me show you one of the graphs that we had before. If I can find it very quickly here. Oh, this one. See, remember this graph? This one, right? If you take, we said that this was a case where the limit did not exist at x, the limit of the function did not exist as x approached 0 from both sides, right? Did not exist. So now, in a case like this, if you take the epsilon to be anywhere here, any in some small value within this region, then when you try to find a corresponding delta value around x, a neighborhood of values within x equals 0, that is, you won't be able to get close to that epsilon. Why? Because the function has a discontinuity there. So you're making this delta values closer and closer to x equals 0, but you cannot get a corresponding epsilon value that would be within this neighborhood of the limit. See, epsilon is an arbitrary small value in the neighborhood of the limit value. If limit function, the value of the function at the limit, the epsilon is in that neighborhood, any arbitrary small value. If the limit exists, you can always find a delta value along the x-axis in the neighborhood of x value such that it corresponds to the epsilon value in the neighborhood of the function value at the limit. That's if the limit exists. But if the limit, such as this one, does not exist, you can pick an epsilon there. But you can't get close to that. You cannot find a corresponding delta value because the function, there is a gap there. In this example, there is a gap there. Therefore, the limit does not exist for this function. So if you pick a small delta value, you're not, or you pick some epsilon value that is sufficiently small. So the epsilon cannot be out here. You can pick it so it's small enough to be in this region, then you will not be able to find a delta that corresponds to it. Why not? Because there is a gap here. So you can find an epsilon for which there is no delta corresponding to it. If that happens, then the limit doesn't exist. Then there's a hole or a gap in the function at that point. But when the limit does exist, such as in this case, then for every epsilon that you pick, no matter how small, you always can find a corresponding delta within the neighborhood of that x value for which you're finding the limit. You can always find corresponding delta for the arbitrary epsilon that you pick. So you pick this and you search for a delta that corresponds to it. If you can find that, then the limit does exist at that point. If you cannot, then the limit does not exist. Okay? So I will say a few more sentences about this, and then we'll do an example. Okay? Oh, so no, that's not what I mean. So let me that. And the key point to remember here, so for any epsilon, no matter how small, a corresponding value of delta. Okay? Again, every time if this, what I've written down, if this is not clear, just go back to these two graphs. Let me put this one back again. Just alternate between these two graphs. See, you can pick a large epsilon, right? We want to pick, so we want to know if this function has a limit as x approaches 0, right? Suppose we want to know that, you want to find that out given this graph. So you can pick a large epsilon here, say from here to here, pick that epsilon, large one, right? Then you can find then a corresponding values of delta would exist. If you pick epsilon large, corresponding values of delta on both sides will exist. But if you make that epsilon smaller and smaller and smaller and smaller, if it's right here, if you pick that so small that it's within this area, then you're not going to be able to find a delta such that it would correspond to this value, to this epsilon value. Remember, this is a function. So if you pick an x value, let's say x value equals 5, you should be able to find what the function value is, right? What we're saying is that if you find a value of the function sufficiently small, let's say we call it epsilon, if there's no limit for x equals 0 here, then you're not going to be able to find a delta that corresponds to that value of epsilon. Okay, so that's for cases such as this one that do not have a limit at, say, x equals 0. But if there is limit, if the limit of this function exists as x approaches 0, then it doesn't matter how small you pick the epsilons along this line. For sure, you can find a delta associated with it. It's the same relationship between x and y, but in this context, we're looking at it in terms of delta and epsilon. And delta and epsilon is any arbitrarily small value of the function. So if the limit exists, you can make the epsilons so small, you'll still be able to find a corresponding value of delta for each epsilon. But if not, then that means the limit does not exist. In this case, it would be true. For any epsilon, very, very small, you'll still be able to find a delta corresponding to it. Let's write this in a mathematical way. Let's do that. So we say thus, or that is, the limit of a function as x approaches to any value a, right? We were using x approaching 0 as an example. But the limit of a function as x approaches in some value a is equal to L if, right? If, this is the important part. If, that's the important piece, if for every epsilon greater than 0. So we said epsilon can be picked arbitrarily small, but it cannot be negative. So just remember that. Epsilon must be some positive value, but it can be arbitrarily small. So if for every epsilon that is greater than 0, but it's very, very small, there is a corresponding number delta also greater than 0, such that if absolute value of x minus a, notice that that's x approaching a, take the absolute value of the difference, less than delta. So that difference is between 0 and delta. So something positive, but between 0 and delta. In the graph that I drew, that would mean x minus a should be in this here and in this neighborhood, here and here. That's why absolute value, right? It should be some distance, which is always positive. That's why we have the absolute value here. So some distance between 0 and delta. Then the absolute value of the difference between the function and L is less than epsilon. And that's L. And f of x equals L. F of x minus L absolute value. So distance between these two is less than epsilon. So that distance can be taken as less than epsilon. So that is just saying this is symbolic interpretation of the graph I had on the other page. So it's just saying that you can pick epsilon to be arbitrarily small here and positive, such that the difference between the function value and that, the absolute value of that distance, is always less than epsilon and corresponds to some number in this interval from 0 to delta. 0 to delta. Okay? If that's the case, then there is a limit. The limit exists. Okay? And by the way, this is called the, let me write this. This is the epsilon delta definition of a limit. Okay? Like I said, your book also has a description, a geometrical description of this epsilon delta definition of a limit. So you're welcome to look at that to see if that is more clear than, if this is what I said is not clear, then you can also read the book. And let me know if you have any questions about that. So here, in contrast to what we showed, so this is when the limit does exist, right? This is the limit when it does exist, and we can take epsilon arbitrarily small, and it would correspond to an arbitrarily small value within this delta distance of x value. But in contrast to that, what happens if the limit does not exist? So in contrast, such as this case. You've seen this graph before, but I wanted to remind you of a contrast between the cases where the limit does exist and where the limit does not exist. So if you try to follow the geometric interpretation of the epsilon delta definition of a limit here with this graph, it won't work because the limit does not exist. So we have this line going that way and another one going this way. And let's take epsilon. Let's pick epsilon very, very small. So between 1 and 2, right? Somewhere there. Like that. And like that. And we want to take, and I'll draw that with a different color here. That. So epsilon would be here, from here to here epsilon, and from here to here again epsilon. Okay, like that. So when a limit does not exist, such as this case, then sufficiently a small value of epsilon, which I've tried to show in this graph, sufficiently a small epsilon, so that the neighborhood delta, and I should show that on the graph as well. Like that. And that would be delta would be this neighborhood and this neighborhood on either side of x equals 0. So if the limit does not exist, then you can find a sufficiently small epsilon, which I did, right? I made sure epsilon is small enough to be in this gap. Because if you pick epsilon large, it won't show you whether the limit does or does not exist. You should be able to pick epsilon as small as you want. In this case, what I wanted was to pick epsilon is small enough to fit in between these gaps, this gap, I mean. Now, find a sufficiently small epsilon, which we did, so that no matter how tiny you make or choose the neighborhood delta, now it doesn't matter how small I make this delta, it's not going to have, once it hits that, it's not going to correspond to the epsilon that is in this gap, right? It's not going to correspond because the function at that point does not exist. And that's what this is saying. So choose the neighborhood delta around x equals 0 then the corresponding range of function values is just too large, right? You can pick that. The corresponding value of delta cannot become smaller than a certain value. So it's always too large for the epsilon that we picked. In other words, there is no limiting value of f of x. Within a distance epsilon of that function value. Okay, so let's look at an example of this before we wrap up this section. And this is the application of the epsilon delta definition. So here we want to, using the epsilon delta prove that, we want to prove that the limit of this function exists at x approaches 4. Okay, you want to show that using the epsilon delta definition, which is what we just talked about, using this definition. Okay, so as x approaches a, the difference that x minus a must be between 0 and delta. As the function approaches L, the difference between f of x and minus L, that difference, absolute value, should be less than epsilon. Okay, so, and these values we should find a correspondence between this and this. That's what we're going to do. If we establish a correspondence, that means that the limit does exist at x equals 4. Okay, let's do that. Okay, so step 1, let epsilon be greater than 0. Some arbitrarily small number that is greater than 0. Okay, let that be the case. In this case, a is 4, right? When I say in this case, I'm comparing it with this. See, a, x approaching a, x approaching 4. So a is equal to 4, and L, in our case, L equals 3. L equals 3. Okay, so that's the step 1. And then step 2, using the epsilon delta we need to find some delta greater than 0 such that if absolute value of this distance, x minus 4, is between 0 and delta, some positive value, then the absolute value of that distance, 2x minus 5 minus 3, is less than epsilon. Okay, we need to show that. So step 3, all we got to do is establish a relationship between this and this quantity. If we show this is equal to that, or something is smaller than that, that's the proof. Okay, step 3. So we know that absolute value of this, take a look at that, we can simplify that, right? And that absolute value of 2x minus 5 minus 3 is equal to 2x minus 8, right, after simplifying. And that is equal to absolute value of 2 times x minus 4, which is equal to 2 times absolute value of x minus 4, isn't it? Right? All of that, all of this reduces to that. And we already know epsilon is larger than that. Okay, epsilon is larger than this. Okay, so thus, let me summarize it. Thus, 2 times absolute value of x minus 4 is less than epsilon. Right? So we just simplified that, and this is what we got. Okay? So step 4. So in this case, the epsilon delta can be written as if absolute value of x minus 4 is between 0 and delta, then this is x minus 4 is absolute value of x minus 4 is less than epsilon over 2, right? From here, we can rewrite it as that. So first we simplified the inside of this absolute value to this, and now we can rewrite this as epsilon x minus absolute value of x minus 4 is less than half epsilon. Okay? So we are showing that there is a value for the value of epsilon that we picked. There is a value within this range from between 0 and delta that corresponds to it. Therefore, there is a limit. Then absolute value of x minus 4 is less than half of epsilon. Okay, that's clear because this is x minus 4, that's x minus 4. If x minus 4 is less than half epsilon, then we found a value within 0 to delta that corresponds to the epsilon that we had. So there is a limit. So let's interpret that. So from here, the last step is the interpretation. Step 5, interpretation. An input value within delta, that's an input value within delta. X minus 4 is between 0 and delta, and its input was or corresponds. I should say corresponds. So this input value, let me make this clear. The input value within delta is absolute value of x minus 4. Okay, corresponds to the function value within a distance epsilon. Okay, right there, it corresponds with half of epsilon. That's the correspondence. Okay, so therefore, thus, we've shown that the limit of 2x minus 5 as x approaches 4 is in fact equals 3. So that's using the epsilon delta definition of that, epsilon delta. Okay, so this wraps up this section, and I thank you for persisting through this video as we introduce the concept of a limit. So for now, have a nice day, and I'll see you all next time.